So our last topic on just looking at electric force and electric fields is what happens with conductors. So we're going to start with an isolated point charge. So this point charge has charge positive Q, and you know it makes an electric field that points everywhere away from it. So the question is, what if we change this? So this is a point charge positive Q, and then we surround it with a sphere. And this is a sphere, not a circle, but a sphere that has some width. And let's start with it being uncharged. So you know the electric field just around this points away from it. But one of the properties of conductors, the only reason it's called a conductor is because it can conduct electricity. Electrons are free to move. So the electrons are going to rearrange themselves. And they are going to keep rearranging themselves depending on the electric field. So we would start off with an electric field like this. But then the electrons in this material are going to say, ooh, an electric field pointing to the right for this one. Well, I'm an electron, so I go opposite the electric field. So it's going to move this way. And enough of the electrons are going to move the opposite direction to exactly cancel out this field. Because eventually, when there's no field, there's no reason for the electron to move. So, first property is that the electric field is zero inside the material of a conductor. So it does this. Remember, this was the movement of electrons. So each one of these is a little bit of negative charge. How much charge? Exactly equal to this. And we get that from Gauss's law. If we draw a spherical surface, let me use black. If we draw a sphere in between here, we know from observation that the electric field is zero. So that must mean that that sphere encloses, by Gauss's law, net flux equals charge enclosed divided by epsilon naught, that the charge enclosed by that black dotted line must be zero. So if this is positive Q here, this overall is negative Q, smeared out all over the surface, but negative Q, exactly equal and opposite. So then on the outside, it's missing electrons. And so if we put the little positive signs, but how many electrons is it missing? It's missing the number that moved, which we just said is negative Q. So if this is missing, the outside surface is positive Q. So if we redrew that picture, what we really should have, pretend these are all concentric, is we have an electric field that goes from positive Q to negative Q, a gap, no electric field, and then the electric field continues. And I can do that in all spaces. Now, this correlates with then to make the electric field zero inside the material of the conductor. So the metal itself has to have an electric field zero. So all charge, all excess charge, must be on the surface of the conductor. So we have negative Q here, and we have positive Q on the outside. So let's talk about more complicated situations. So if we have a point charge here that's positive Q, and we put a spherical shell around it, well, because of Gauss's law, electrons are going to be pulled to the inside to cancel out this positive Q. So we have negative Q on the inside surface, so now there's no electric field in this area. But let's say initially this thing, overall, the shell, had a charge of positive 5Q. So it had positive 5, but now it's got negative 1 in the middle. So there now has to be an extra Q on the outside to cancel out this negative to give the original positive 5. So we would get, if I just do 1, 2, 3 lines, then we'd have 1, 2, 3. Because we have 6, I need to have 1, 2, 3, 4, 5, 1, 2, 4, 5, 1, 2, 3, 4. So notice a general rule. If you know the initial two charges, the central object and the outside object, the inner surface has to cancel out the central object. So if this is positive, this is negative, exact same amount. The outer surface ends up being the sum of the original two. So let me write that down. Shell inner surface equals opposite of central charge, and shell outer surface equals the sum of the central and shell initial. Another way of saying this is, if I start off with two separate objects, one's positive 5Q, the other one's positive Q, and I only measure the electric field on the outside, all I'm going to know is the total charge enclosed is positive 6Q. I don't know that it was originally 5 here and 1 here. I just know I've enclosed a total charge of positive 6. So on the outside, we see big picture. Just add it together. We don't know where it is. On the inside, in this air cavity, they have to cancel each other out, because once you move away from the center a little bit more into this material, there cannot be an electric field after it reaches equilibrium. So 2 more things I want to remind you about the idea of grounding and connecting. These electrons came here because they couldn't get any closer to this. There's a gap, they can't get there. So if we were to connect a wire here, they'd have a path to cross. And so both of these would then become neutral because they were equal and opposite, so then both surfaces would be 0. But this positive 6 would still be on the outside. If, on the other hand, going back to this picture, if we ground the outside, remember grounding means connecting to basically neutralize something, only the outer part is grounded, so the 6Q would go away. These two charges would still be separated, but we wouldn't know that from the outside, because outside it says there's no electric field because this charge is gone, so there's no charge enclosed. That means no net charged enclosed, equal number of positive negatives. That's one of the reasons I needed to say up here all excess charge must be on the surface. This metal is full of protons and electrons. There's lots of charges throughout here. But if I put extra charge on there by adding electrons or taking electrons away, thank you, Benjamin Franklin, then that excess charge must be on the two surfaces. It cannot be inside the actual material of the metal. So I'm going to ask you some questions on, if you start off with these two charges, what do you get here? Or I could ask you in any combination. I could tell you, if you end up with these two, what is this? Or if I tell you these two, what was this? And you would always use just these two rules. The shell inner surface is always equal and opposite the central charge, and the outer surface is the sum of the two charges. I also am going to ask you to calculate the electric field at different distances. Well, at any distance from the center inside this point, so any place in here, the electric field depends only on the central charge. If we're in the material, the electric field is 0. If we're outside both objects, then we calculate the electric field based on the outside surface charge, which is the same as the two initial charges added together. So, not hard math, but a little different way of thinking about things.